Next slide. Now we move to the last 10% of a star's life to look at the elderly and dying stages. The great majority of stars in the galaxy are low-mass stars, less than about 6 or 7 solar masses, and they die in this way. They bloat outward to form a red giant and eject their outer layers to form a planetary nebula, while their cores shrink to become a white dwarf that slowly cools off. So right now, the Sun has a hot core and warm 5800 Kelvin surface, and it is only 109 Earths in diameter. About 5 billion years from now, the core will stop fusing and shrink. As the core shrinks, it heats up greatly. Eventually, the layer just outside the core, called the shell layer, gets hot and dense enough for fusion to start. This fusion is very rapid because the shell layer is still compressing and increasing in temperature. The luminosity of the star increases from its main sequence value. The gas envelope surrounding the core puffs outward under the action of the extra outward pressure. So the surface will bloat outward, cooling off the surface as it does so, to make a red giant over the next couple billion years. The Sun will become at least 700 Earths in diameter, swallowing up Mercury and Venus, and maybe Earth too. Although it is large in diameter, it will have less mass than it did during the main sequence stage. Stars lose mass as they live out their lives. Despite the cooler surface, it will be much more luminous than during the main sequence stage because of its huge surface area. The Sun's increased luminosity will heat the Earth's surface so much that the oceans and atmosphere will evaporate away. A red giant has the extremes in temperature and density. Its surface is cool and very low density, while its core is very hot and extremely dense. The following 9 slides step you through the dying stages of the low-mass stars. The captions will describe what's going on. At the end of the main sequence stage, the nuclear fusion fuel runs out in the core. The core contracts and heats up. The shell layer outside of the contracting core begins fusion. The increased energy from the center pushes out the outer layers. The low-mass star becomes a red giant. Only the very massive stars become a supergiant, and we'll look at those in the following week. Notice how the dot for the core has gotten smaller while the outer layers have gotten larger, but less dense. Big does not mean massive. If the star has enough mass and can raise the core temperatures up to the 100 million Kelvin needed to fuse the helium, core fusion will begin again. The helium fuses to create carbon and oxygen. This core fusion stabilizes the star, and the star shrinks back to a new equilibrium state that is larger than the main sequence stage. Eventually, the helium runs out in the core, and the core contracts and heats up. The shell layer outside of the contracting core begins fusion. The increased energy from the center pushes out the outer layers. The low-mass star becomes a red giant again, not a supergiant. For the low-mass stars, this is it. Next slide. In this next to last stage of a star's life, the outer layers are ejected as the core shrinks to its most compact state. A large amount of mass is lost at this stage as the outer layers are returned to the interstellar medium. For the common low-mass stars, those less than about 6 or 7 solar masses, the increased number of photons flowing outward from the star's hot, compressed core will push on the carbon and silicon grains that have formed in the star's cool outer layers to eject the outer layers and form a planetary nebula. The ultraviolet light from the hot, exposed core, called a white dwarf, causes the gases to fluoresce. Many planetary nebulae will have thicker-looking boundaries and more transparent centers because of what I call the soap bubble effect. More gas is seen along the line of sight at the edges of the shell, so the shell appears more transparent when looking through the center. In some cases, the mass loss is really asymmetrical to produce things like the cat eye nebula or the hourglass nebula. The textbook has even other interesting shapes for planetary nebula. Next slide. For cores less than 1.4 solar masses, the core collapses to form a white dwarf. You have something with as much mass as the Sun shrunk down to the size of the Earth. The more massive white dwarfs are actually smaller because they are more compressed. Electrons run out of room to move and hold up the dead star against any further collapse. This graphic shows the three core remnants possible with the white dwarf on the left. We'll talk about neutron stars and black holes in the next lecture. Note that masses given here are just for the core masses, only after all the outer layers have been ejected. Obviously, the white dwarf is incredibly dense. A sun per Earth volume, which equates to 1 teaspoon of the white dwarf material, would have a mass of 1 ton. Next slide. This last slide covers how we've been able to confirm our models of stellar evolution. We use star clusters for several reasons. What is nice about clusters is that differences in the stars can be explained in terms of only one variable, mass. Stars in a cluster all form at about the same time, so age differences is not a factor in our analysis. The stars form from the same gas cloud, so their chemical composition is the same, and all of them are at about the same distance from us, relative to their huge distances from us. So any differences in apparent brightness are due only to luminosity differences. Recall that more luminous main sequence stars are more massive than dimmer main sequence stars. Comparison of the models with reality is easy since you need to only consider how mass affects the cluster star's evolution. The predictions from the stellar evolution models as to what the characteristics of the stars in different clusters should be are compared with reality. Star formation and stellar evolution models are confirmed by observations of real clusters. By observing clusters of different ages, you can piece together how a star will form, live, and die. The pictures step you through how the cluster's properties on the HR diagram change through the years. We create computer stellar evolution models of a star cluster with the proper proportion of lower mass stars to higher mass stars, and have the computer simulation run through the life cycles of the stars of various masses. When we compare what the computer models predict for the luminosities, the magnitudes, versus the temperature, the color, with real clusters in the galaxy, they match up. The star formation process begins at about the same time in a cloud. The lower mass protostars are still collapsing when the massive stars begin nuclear fusion. Notice that the protostar will have greater luminosity than the main sequence star it will become, even though it is cooler because of its large surface area. The dots in the HR diagram are above, more luminous than the dashed main sequence line. As the cluster ages, the massive stars die, leaving just the less massive stars still on the main sequence. Like peeling a banana or burning down a candle, the arrows in the HR diagrams mark the main sequence turnoff. The main sequence turnoff is the mass of the most massive main sequence star remaining in a star cluster. The turnoff mass gives us the age of the star cluster. It equals the lifetime of the most massive star still in the main sequence stage. At the end of the slide is a link to the beautifully illustrated guide for teachers, students, and the public called An Ancient Universe: How Astronomers Know the Vast Scale of Cosmic Time, put out by the American Astronomical Society and the Astronomical Society of the Pacific.